And now in this final part of the imaging lecture, we will cover the non-ionizing radiation imaging, starting with MRI. You see, it's a beautiful paper in 2019 showing the 7 Tesla MRI scan of a full human brain. This image took 100 hours, and you see the scan of the full human brain. You see now, I mean, we are approximately in the middle now of the brain, and then you will see the image shrink because you go on the other side. So MRI is becoming more and more a leading technique in imaging, more and more used, more and more applied. There are also MRI linacs now where you can actually give radiotherapy together with MRI to follow the movement of the organs. The ability, the big difference is that, of course, as much as radiography is good in visualizing bones, let's say hard tissue, because you use absorption of X-rays, MRI instead essentially only visualizes soft tissue and is particularly good in visualizing soft tissue. So the idea here is originally was called nuclear magnetic resonance, because it is actually the resonance of the spin of the nucleus. So it is known, you know, that every nucleus has a spin, and the nucleus has Z protons and then neutrons, and actually each nucleon, of course, has an intrinsic angular momentum, which is associated to a quantum number. The magnitude of the angular momentum is very well known. It's this famous quantum mechanics formula. And the magnetic moment can be expressed in this way: E divided by mp times s, where s is the angular momentum associated to the mass of the proton. And this means 5.05 per 10 to minus 27 joule per Tesla. Now, essentially, what is the idea here? I mean, in the nucleus, the spin of the different nucleons couple with each other. So, if you have nuclei with even Z and even N, you will have the total value will be 0. But nuclei with even odd Z and odd even N will have 1/2 3, and the other way around, odd Z and odd N will be 1, 2, 3, 4, 5. So these are integer, and these are even odd or odd even. So, for example, for hydrogen, the spin is 1/2. For carbon, the spin is 0, of course. Of course, not for the isotope, but for the carbon 612 is 0, and then you see for sodium 23 is 3.5, and so on. So if we take an arbitrary volume of the body tissue, each nucleus has its own magnetic moment, but the direction of the spin is randomly oriented, so the total spin in every part of our body is always 0. There is not a specific magnetic field. This is, of course, I guess, well known from statistical mechanics. Now, the idea, what is here? Now, the idea is to impose now a magnetic field, an external magnetic field. And in this case, as you know, all the spins, this is the same thing in a magnet. You know, when you have a paramagnet, let's say, not a diamagnet, but if you have a paramagnet, all the different spins will align and they will actually rotate around the main axis with the Larmor frequency, which is given by this formula, where B is the external field and gamma is the gyromagnetic factor of the atom, of the nucleus. Now, this is an example. Of course, you must have an odd number of protons or neutrons. One of the two has to be odd. And then you already see that hydrogen is ideal, because most of the elements in our body have the same number of protons and like in this case. I mean, these are not very common, but for hydrogen, which is extremely common in our body because it's in water everywhere, the spin is 1/2. At 1.5, the gamma is 42.58 megahertz per Tesla. And at 1.5 Tesla, you have a Larmor frequency of 63 megahertz. Now, what is the idea now? The aligned, these nuclei will align on the magnetic moment. They will have an energy, of course. The energy of the magnetic moment is minus μb, or given by this formula. And so they have essentially two energetic states. They are in one energetic state or another energetic states, where the spins are parallel, or the spins are anti-parallel, with minus or with plus. These are the two possible energetic states of the system of the spins, and this is the transition here that we want to exploit. So essentially, you can write the energy difference as gamma h cat times b. And you can have transition between these two excitation levels by absorption of the photon in the right range. The photon energy if you look at the formula, is directly correlated to the Larmor frequency, because gamma b is the Larmor frequency. So if you have a gap in energy, which is given by h cat omega 0, this energy of the Larmor frequency is either absorbed or emitted in a transition between these two excited states. So if you remember here, we saw that this frequency for the hydrogen is 63 megahertz is the Larmor frequency, times the Planck constant divided by 2 pi gives you the delta E. So the transition process are shown here. You have a spin-up state. Now you have a resonant absorption of and the proton spin is inverted. And then the other way around, the loss of energy, now you will have the emission of a photon from this state to this state. You can go back to the high energy state, to emitting this photon to the lowest energy. I'm sorry. So the two spin states are differently populated as a consequence of applying an external magnetic field. After a certain relaxation time, the population of the two levels will reach an equilibrium, which is determined by the temperature and the energy difference between the two states. Because of the higher excitation energy, the upper state is less favored. So the population ratio is given by what is called the Saha equation, which gives a typical equilibrium equation. So this is how they are populated, where K is the Boltzmann constant, Ts is the temperature, and N up is the number of the nuclei in the spin up, and N down is the number of nuclei in the spin down. So these are parallel to B, and these are anti-parallel to B. So that's the story now. You go into the excited state. There is only minor difference in the population of the lower and upper level. For 10 to the 25 protons, there is only an excess of 10 to the 6 in the lower level at room temperature, according to the Saha equation. But this difference results in a net spin-up alignment, which causes a magnetization of the material in the external magnetic field B. Now, this allows to discriminate one element from another using nuclear magnetic resonance signal. Why is that? Because each element has a characteristic energy difference between the spin up and spin down, which correspond to its characteristic Larmor frequency. So the MR signal is the result of the excitation of the spin down states using a radio frequency. So you give a radio frequency energy pulse of specific frequency. This energy absorption causes the displacement of the net magnetic momentum from its normal equilibrium distribution in the external magnetic field towards the population of the higher excited spin down state. So that's essentially what happens now. As the system, after the pulse, you see here, as the system returns to equilibrium by de-excitation, MR signals are emitted in proportion to the number of excited nuclei in the sample until the equilibrium is reestablished. Now, this time, let's say that this relaxation time is called the relaxation time, and is divided in longitudinal T1, this is the one in direction of the magnetic field, or the transverse, which is in the plane, which is perpendicular to the direction of the static magnetic field. So at the end, the absorption and subsequent emission process take place only at a certain frequency, at the Larmor frequency, and that particular frequency is called the magnetic resonance of the isotopes. You know, that's exactly the only point where you can have detection and acquisition of the nuclear magnetic resonance signals at the characteristic Larmor frequency constitutes the basic information for spectroscopy and imaging. So these are now, what you exploit here now is the difference T1 and T2 for the various tissues. You see, for example, for the fat tissue, these are the values of T1 at 1.5 Tesla. This is the value of T1 at 1.5 Tesla. You see, they are quite different. And this is the value of T2 for different tissues. All of them must be tissues rich in water, because you need hydrogen. So you have fat, liver, muscle, white matter, gray matter, and cerebrospinal fluid. So this is what you use. The display of the images is a multiple set of gray tones. Visualization and interpretation of the multi-parameter images may be optimized by assigning a color tissue segmentation. You see here that using the color segmentation, you see much better the image that comes out. The system is quite complex, of course, because you must have, you see, this is where the patient lie, and you will have a magnetic static field, gradient coils, the radio frequency head coils, and then you have a very complex control system, you see, that gives eventually the image in the different computers. And that's how you control the scanner by pulse sequence, where essentially you give the radio frequency pulse, you take the image, and then you move the patient to go on in the image acquisition. So for the T1 weighted sequence, so T1, if you remember, is the one perpendicular along the field. You will have this kind of image when you have when going from it will be black for air, calcium, cortical bone, and rapidly flowing blood. And then you go down to white. You see, when you go, white will be fat, blood, gadolinium, which is a contrast, agent, melanin or protein, and here you have high protein tissue will be gray, and fluid will be more on the black region. So you see how the air will be essentially all black, but you see clearly the muscle, you see very clearly the fat, and you see the cortex. Let's say this is the bone marrow, and this is the fluid surrounding the bone marrow. If you go in the T2 here, this is even more interesting, because you see this is the different colors. As you see, this is a T1 and this is a T2. T2 is particularly dependent on water, so the amount of hydrogen essentially that you have in your tissue. So when you have an edema, which is very often associated with many pathologies, many pathologies, for example, involved in abdominal pathologies, always give edemas, but also if you have a head, if you are hit in the head, you will have an edema. Then the T2 sequence is very suitable to detect pathological situations. And then there is another way, which is called PD. This is the proton density weighted image that really only visualizes the number of protons. So now you really go only with the number of protons. It's called the PD weighted image. And here the tissues with few protons have low signal intensity. Tissue with many protons have a high signal intensity. This is it. This is an example, for example, of the meniscal tears. The PD weighted image in sagittal direction of the knee in two different patients at the level of the medial meniscus in the knee. Left show an intact meniscus. At right, here there is a tear in the posterior horn of the medial meniscus, and you can also see the fluid, the Hydrops and Baker cyst that have intermediate signal intensity on the PD here. Okay, so there are many MRI sequences that you can exploit, you see, for visualizing different objects. If you want to see normal anatomy, then probably T1 is the best. If you want to see pathology associated to edema, then T2 is the best. If you want to look at meniscus or gray and white matter, then it's better the proton density. But then there are many others. You see some of them, like FLAIR is a T2 weighted image with selective suppression of the cerebrospinal fluid signal. This is much better for detection of white matter abnormalities. You can use gadolinium that reduce the T1 relaxation time to detect and characterize lesion, and for angiography to do it live. There are many other different sequences. Of course, if you look at this formula that gives you the thermal equilibrium, spin polarization is here, is given by this formula. This is when they go in thermal equilibrium. This all depends, of course, on the intensity B of the field. So it is particularly in the T2 weighted MRI imaging that you benefit from ultra-high field strengths. That's an example. This is how the brain looks like at 1.5 Tesla, and that's how it looks like at 7 Tesla. Look at the zoom. Look now how much detail you can have here. 7 Tesla was actually introduced in 2017. It's not everywhere, but there are in several hospitals. Research models are already working at 11 Tesla. So this is quickly growing. The problem is the cost. You see, a 1.5 Tesla machine, like this Magnetom by Essenza, is about Magnetom Essenza. This is all machines by Siemens. These are all Siemens machines, so same company. 1.5 Tesla, 300,000 euro. 3 Tesla, 2 millions. 7 Tesla, 7 millions. So you see that the price goes up quite a lot with the magnetic field, and so is the size of the machine. If you look at the size of this machine, and this machine, you see how bigger and bigger they become. But these magnetic fields can also give indication for what is called functional MRI. So not only to see the anatomy of the brain, but also to see the activity of the brain. This is really something fantastic. It is used since a long time. It measures the metabolism, which is correlated to the neural activity. And what is really measured is changes in blood oxygenation. So what this is called the so-called bold contrast. So if you have resting neutrons, you see you have this will be the situation. This is oxygenated hemoglobin, and this is deoxygenated hemoglobin. When you have activated when you have activated neurons, you will now have you see the density here, the density of the neurons here. You will now need more oxygen, so you have a change in the oxygen consumption. So essentially what you measure is the blood oxygenation level dependent contrast, so-called BOLD. And so this way, you see, you can use MRI to study brain function. This is one of the first paper, the paradigm shift study, published in PNAS, the Proceeding of National Academy of Sciences, on 1992. For the first time, they were able to show, you see, using photo stimulation, the visual cortex, the activation of the visual cortex. You see here, this is the visual cortex. You see the deep activation of the visual cortex when you have exposure to light, using this bold sequence. The key concept, of course, are contrast, spatial resolution, temporal resolution, and functional resolution. What means the functional resolution? The contrast to noise is critical for functional MRI, because how effectively can we decide whether a given brain region has property X or Y? You know, it's you see how this is now the so-called functional contrast to noise, and in functional MRI is really critical. The spatial resolution is also important because it gives you the opportunity to identify which areas in the brain are involved. And you see how the typical functional volume voxel is about 4 cubic millimeters. So it's not very high, it's not a very high resolution, of course. And of course, the temporal resolution, because you have to see how this evolves in time, how is the response evolving in time, and the functional resolution, so the ability of measurement technique to identify a relation between a neural activity and a cognitive or behavioral phenomenon. There are many examples of this. This is one I just picked from an old paper in reading versus web surfing. So this is the same subject, which is reading a book, and here is surfing the web. So look at the difference in how many more areas of the brain are activated when you're surfing the web compared to reading. Finally, the final technique that I want just to briefly touch upon is ultrasound, of course. Ultrasound, that again is used very much, as you know, in gynecology for monitoring the uterus during pregnancy, which is now gives this beautiful 3D ultrasound images of the baby, but it's also very much used in diagnosis of different disease, including oncology. You can use ultrasound to see, for example, liver metastasis here. Ultrasound is nothing else than a sound, but at the frequency of the order of kilohertz. Actually, in medical application, you use megahertz. The speed, as you know, is about 1500 meters per second, but depends on the tissue, of course. In the lungs, because of gas, the propagation speed is lower. In bone, because it's a solid, the propagation speed is higher. So the ultrasound doesn't penetrate lungs and bone very well. So you have to, the change in velocity, let's say, gives you this problem. There are different types of ultrasound. You generally use pulsed ultrasound, a few cycles, produce it by applying electric pulses to a transducer. at boundaries between structures, for example, between different tissue types, waves are partially reflected. To determine the distance, so to convert it in an image, we need to know the propagation speed, the pulse round trip time, so from signal emission to echo detection, ultrasound imaging is also called echography, and then to determine the distance, just using this normal formula where you have that the velocity will be 2d divided by t, where d is the propagation distance and t is the time, and 2 because you have the signal arriving and the echo coming back. And then you can calculate the distance using simply this formula. So as the round trip increases, reflector distance increases as well. This is, you see, the example for 130 microsecond, 39 microsecond, 13 microsecond, depends on what is the depth that you are going in. And then you can do the imaging, because the ultrasound pulse simultaneously encounters several scatterers, so several echoes are generated simultaneously. So you have an interference now of the echoes coming from the pulses and the echo of the pulses. And this interference produces a dotted pattern, the so-called speckles. So does not directly represent echoes, but rather how they recombine in the detector. So what you see here, the image with ultrasound is sometimes very difficult to read. Not so much here. I mean, here you clearly see the baby, but that's because the speckles represent the interference of the ultrasound of the images. With this, I'd like to close. Thank you very much. And we will see nuclear medicine in the next lecture.